Hey there, and welcome to the Explainer. Today, we are cracking the code on chemical reactions. We're going to move past just asking how fast to a much more powerful question. How much is going to be left and when? I mean, think about it, right? How long does a medicine actually stay effective in your body? How long until some radioactive material is safe to be around? To answer questions like these, you have to be able to look into the future of a chemical reaction. And the tool that lets us do this, our, chemical crystal ball, is the integrated rate law. These are the powerful equations that connect the amount of stuff you have left with how much time has gone by. Okay, so let's really dive into this. If we want to understand a reaction's journey over time, we need to think about its speed a little differently. Here's a super simple way to picture it. A regular old rate law, that's like your car's speedometer. It tells you your speed right now. But an integrated rate law, that's like your GPS. It takes that speed and predicts exactly where you're going to be down the road in an hour. It's the huge difference between your current speed and your final destination. So for this explainer, let's pretend we're on a mission. We are chemical detectives, and our one and only goal is to uncover a reaction's true identity. In chemistry, we call this its order. And trust me, once you know the order, you basically know all its secrets. Now, the good news is that in most cases, there are really only three main possibilities for a reaction's identity. So let's meet our three usual suspects. Here's our lineup. We've got zero order, first order, and second order. Each one of these has its own unique personality, a totally different way it behaves based on how much reactant you've got left. So here's what makes them different. A zero-order reaction, its rate is constant. It just chugs along at the same speed, totally ignoring how much stuff is left. A first-order reaction, though, is directly proportional. You double the concentration, you double the speed. Simple enough. But second order is the dramatic one. You double the concentration and the rate quadruples. It's way more sensitive. So how do we tell them apart? How do we identify our culprit? Well, as detectives, we have one primary technique, and it involves looking for a single, crucial piece of evidence. Our secret weapon is all about the graphs. See, here's the magic trick. Each one of our three suspects has one and only one specific way of plotting its data that produces a perfect straight line. What's so amazing about this is that we're turning some really messy calculus into a simple visual test. Find the straight line, and you've found your answer. Okay, let's work a real case. This is actual data for a reaction of a molecule called butadiene. We've got our clues right here, a series of concentration measurements taken over time. Time to start the investigation. All right, let's start with our first suspect. Could this be a first-order reaction? Now, the detective's handbook says that for a first-order reaction, if you plot the natural log of the concentration versus time, you should get a straight line. So, let's see what the evidence tells us. And there's our result. Whoa, that is definitely a curve. Since this plot is not a straight line, we can say with 100% certainty that this reaction is not first order. Suspect number one is officially in the clear. So what's next? Let's move on to our other main suspect. Could it be second order? Now, the test for a second order reaction is different. We have to plot the inverse of the concentration. That's 1 divided by the concentration against time. Is this going to be the one? And bingo! Would you look at that? A perfect, beautiful straight line. The evidence is undeniable. The dimerization of butadiene is a second-order reaction. Case closed. We have found its true identity. Now that we've identified our reaction, we unlock one of its most important and useful characteristics, something called its half-life. The half-life is pretty much exactly what it sounds like. It's the time it takes for exactly half of your reactant to get used up. You can think of it as a reaction's own little signature countdown clock. And here's the really crucial difference. For first-order reactions, things like radioactive decay, the half-life is constant. It always takes the same amount of time to go from 100 grams down to 50 as it does to go from 50 down to 25. But for zero and second-order reactions, that's not true. Their half-life is variable. It actually changes as the reaction goes on. That's a huge distinction. Okay, wow. We've gathered a lot of clues, we followed the evidence, and we solved the case. So let's compile all of our findings into a single, powerful final report. This right here is it. The ultimate cheat sheet. This table is your field guide. It tells you exactly which plot to make to get that straight line, what the slope of that line tells you, and the specific half-life equation for each order. This is the master key to everything we've talked about. So, if we boil it all down, the main takeaway is this. That simple act of finding the one linear plot tells you the reaction's order. And once you know the order, you know everything. You know which equation to use, you know how its half-life is going to behave, and you can predict its entire future. We've totally cracked the case of how a reaction behaves over time. But we haven't really touched on the why. What sets that speed limit in the first place? What's the secret behind that rate constant, that little k? And what happens if you, say, turn up the heat? Well, that is a whole new mystery, and a case for another explainer.